here is show you how we can apply some of the materials, concepts, and ideas we've learned in chapters 1, 2, and 3 to some actual data that would be similar to the data a political scientist would use. Now, the population, the thing that we want to know about is all students in POS 401 Summer B session. And there are about 60 students in the course. However, only 51 students took the survey. So we do have a sample of the population. And we should also note that the sample is not entirely representative of the population because some people self-selected not to take the survey. And if those people differ, the people that chose not to take the survey, if they differ in any way from the people that did take the survey, then our results would be biased. We also assume with survey data that people answer honestly and truthfully, right? And we do know, survey researchers, we do know that that is not always true. In fact, it's often not true. But that's material for another course. Now, what I've done here is I've taken the responses from each student, and so you can see each row would be a student. And I just have labels here for what the questions mean. They're kind of generic labels. And this is in an Excel sheet or open office spreadsheet. And all your responses are anonymous, right? There's nothing here that tells me who took what survey. I have the country you took it from and the state, but that's it. And everything's just a bunch of numbers, right? Everything's just a bunch of numbers and rows and columns. And what this really is a matrix, right? It's a huge data matrix, which is why matrix algebra, college algebra is so important for social scientists, is because the data we use, such as this, is really just one big matrix of numbers, right? This column here is a vector, and this whole spreadsheet is really just a big matrix of values. So what we do in statistics is really just a lot of matrix algebra. Okay, so I'll close that out. What I've got here showing you is what says R console. This is a statistical software package that's free that a lot of social scientists use. It's one of many packages that I use. The nice thing about it is it's free. It does a lot of stuff that I want it to do. It makes nice, pretty graphics. The bad thing about this program is it's pretty complex to learn. The startup cost to learn it is high. You can't just point and click. You really have to actually write code. What you've seen I've done here in this second sort of text document, I just have a bunch of code that I've rewritten for this exercise. And if you really did want to learn R, and it's a nice skill to know, I recommend starting with this book, Political Analysis Using R from James E. Monaghan on Springer. This is a really good book written by a political scientist that will sort of walk you through how to download R to your computer through doing sort of basic techniques of statistical analysis that we'll learn in this course. And again, R is a great skill to learn. It's very high. It's in high demand on the job market. People from data companies in Silicon Valley to corporate companies are using programs like R and SAS and Stata to analyze data, just like we'll learn how to do a little bit of in this course. So what I've already done here is I've loaded the data, and you see all the different variables. You sort of get descriptive statistics on here. Let's just play around with a few basic things. Let's look at gender, right? And so if I type in gender here, we see what the actual data is. This is just that vector column of are you male or female? And it's in a bunch of ones and twos, right? So 1 would be male, 2 would be if the respondent said female. And we might want to take the mean, right? We've learned how to calculate the mean in this course, and you have a mean of 1.35, right? So what does that mean? What does it mean that the mean of gender is 1.35, right? Well, it doesn't really mean anything, right? There's no 1.3 gendered on your biological sex, right? What it's doing is the computer's basically taking these ones and twos and calculating the mean, what you told it to do, not realizing that what you told it to do was something pretty stupid and meaningless, right? If you do the medium, right, the same thing, you get a 1. That actually has some meaning, right? It means the median person in the sample is a male, right? And if you take the mode, right, what's the most common value, you get a 1 as well. So what we can see here is that the way that we've measured this concept and the way that this concept of gender exists in the world, in the population, between people being male and people being female, right? this leads to a discrete variable, right? So the chapter talked about discrete continuous variables. Here we have a discrete variable. We either have one category or another category, right? You're either male or you're female. And so because of that, taking the mean doesn't really make much sense. Having the median or the mode in this example are better measures of the middle, better measures of central tendency that actually have meaning to the concept, right? Now I don't like the bunch of the ones and the twos, so what I'm going to do here is just add labels to the gender variable, and I'm adding labels to the vote choice variable of are you going to vote for Clinton or Trump. And then what we could do is we could make a nice table, a frequency table of gender. We can see that there's 33 males in the course, or 33 males in the sample, I should say, not the course, and 18 females in the sample, right? So that's just our frequency table. We might want to say, well, what's the proportion there? So we do a proportion table, and we just have 64% men in the course, almost 65 if we round, and 35% females in the course. So that gives us a better idea than sort of the raw values of what the ratio of sort of men to women in this course. And you can conclude from that maybe that, that there's an underrepresentation of women in the course. And if you want to maybe make an inference that there's an underrepresentation of women at ASU, thinking about ASU as the population, and this just being a sample, you would actually be correct. There's actually 56%, so 56% men versus 43% women in the official ASU enrollment numbers. So the sample here, which isn't a good sample of ASU, right? If ASU was our population and we only sample people in POS 401, that's an unrepresentative sample. We get the wrong answer, right? We're about 10 points off. We're overestimating men by about 10%, underestimating female enrollment by about 10%. But the actual conclusion we reached, that women were underrepresented at ASU, is actually correct, right? So taking a sample can tell us something about the world, about the population. It doesn't always give us the exact correct answer, but we can be in sort of the ballpark. Now, if we took a more representative sample of all students at ASU from different classes and majors, we'd probably get something closer to the official numbers. And I'll just post that here so you can see it, right? 56% male for 43.8% female. Okay. So then let's look at vote choice, right? So who are you going to vote for on election day, Trump or Hillary? 29 people said Clinton and 20 people said Trump. We could look at a bar plot, right? A bar plot, because this is also discrete data. It's two categories, Clinton and Trump. That's discrete. And we can look at this bar plot here, and let's just resize it. And here we can see that same data, right? 29 people are going to vote for Clinton, 20 are going to vote for Trump. And what we want to do here is we want to see the x-axis here at the bottom, right, is vote choice, Clinton, Trump. Those are labeled. And then here we have the frequency, right? We're talking about a frequency, which is just the number. And we could do the same thing for gender, do a frequency table or bar plot, right? And we can see how many men and women are in the course. And as you can see already, hopefully, that looking at some visualization of data is often better than looking at, say, a frequency table as we're doing over here. Okay. So then we might want to know, are men more likely to vote for Trump or women more likely to vote for Hillary? So then what we could do is a bar plot such as this, right, where we break down the discrete data into different categories. So here we have the number of men who are going to vote for Clinton, the number of men that are going to vote for Trump, the number of women that are going to vote for Clinton, and the number of men that are going to vote for, the number of women that are going to vote for Trump. And you can see the legend here, which you're probably familiar with. Now, that figure doesn't really tell us if women, say, are more likely to vote for Clinton and men are more likely to vote for Trump. What we want to do is change that into a percentage or a proportion, right? So what I've done here is change it into a percent. So here we have now the y-axis here is changed. So instead of a frequency, it's the percent supporting Clinton. And here we have a little under 60% of men who support Clinton. And here we have a little more than 60% of women who support Clinton. So we do see some relationship, probably potentially some sort of association between gender and which candidate you're supporting during the election. So this is a nice, more informative graph than just the frequency distribution. One of the things that sort of makes statistics in this course hard is there's no there's lots of options, is what I should say, right? There are wrong choices you can make in how you present data and what statistics you run. But there's also no single right way to do it. So there's lots of different ways which we can present this data. So here I'm going to give you a mosaic plot, which I think shows this data in a much better fashion. So the mosaic plot is like a bar plot. What we have here is this column is for men, this is females, and here we have vote choice, right, along the rows. And so what you see here is that the bar for men is much larger than the bar for women, right? It's overall much skinnier here. This basically gives us a way to just visualize at this chart and see right away that there are more men in the class than women, right? We can also see that there's more men who are going to vote for Clinton than men that are going to vote for Trump, and more women that are going to vote for Clinton than women that are going to vote for Trump. But we could also see by the breakpoint, where these breakpoints lie, that, well, men are more likely to vote for Trump than women, right? So you sort of get all the information about the frequency of each variable, right? As well as sort of the different proportions of those variables, all in one plot with a mosaic plot. Okay, so those are discrete variables. Then what I've done is I've created a variable called moral traditionalism. And moral traditionalism is essentially a value that an individual might have towards holding on to traditions of the past. And so I had students in the survey answer a series of questions about, do you believe the world is changing and we should adjust our moral behavior to those changes? Or should we be more tolerant of those who live according to their own moral standards? And what these questions do is they measure this is who values traditionalism and who does not, or who values it less. And I've combined these questions into a single indicator. And so we can look at that here. Let's type in moral traditionalism. And you can see the different values, right? You get sort of different values. Now, in reality, these are ordinal values. They're not entirely continuous because they don't range from, say, they can't really take on every value, right, because of the way that they're measured. But we can think of the latent concept that it's measuring as a continuous measure. And so for our purposes, we're going to treat this as continuous. Those of you that are going to be nitpicky and say, well, this really isn't continuous, you're right. But we can pretty much treat this as a continuous variable without running into problems. So then for a continuous variable, we don't want to do a bar plot. That wouldn't make sense. Instead, we run a histogram. Right? And so here you can see the histogram of moral traditionalism. Now the scale runs from 1 to 5. People that score 5, these people value traditionalism and traditional morals and values and culture. And people that score 1 do not, right? Or they value them less. Right? And this is the frequency. So this is the number of people. So we have, what we can see here is about 5 people who we would say do not value moral traditionalism. And here we have 2 people that really do value moral traditionalism, with lots of people in between. This would be the modal category, right? The category most selected most frequently would be sort of this 2.5 to 3. Okay. Now, what if we run a histogram with discrete data, right? So let's run gender with discrete data. Well, what I do is I get an error, right? It tells me it must be numeric. And so this program is actually pretty smart in that when you do something wrong, sometimes it'll say you're doing something wrong. You get these nice things in red. Lots of programs won't do that. So you as the analyst really do need to know that it's not right to run a histogram on a discrete variable, and that when you have continuous variables such as moral traditionalism, that the histogram is the right plot. We could also run a scatter plot with moral traditionalism, right? And so this gives us the respondents on the x-axis. So this is respondent 1. And respondent 1, the very first person that took the survey is this dot here. And this person is scored pretty high on moral traditionalism. The last person that took the survey, number 51, is here right in the middle of the moral traditionalism scale. Right, and what you can see here is that people are kind of spread out all over, but you can see the bulk of this responses are sort of in this middle area here, and slightly downward, right? As we saw, we actually get the histogram was a much better picture of that. Okay, so then we might ask, what's the distribution of moral traditionalism by gender? So then we can do the box plots that we saw in chapter 3, and these give us men, women. This is the moral traditionalism scale. This box tells us where sort of the bulk of the data is, where the sort of 50% of the distribution is, with the lines telling us where I think it's the mode or the medium. One of the measures in the middle, you can consult the textbook to see exactly what one it is. So here we see that women are a little less, value moral traditionalism a little less than men. But overall, I wouldn't say there's a big difference there. But the distribution is very different, right? So we saw in the textbook that these box plots show us sort of the interquartile ranges, the 25, the 50%, and then the 75% interquartile ranges. So we can see that the spread here is much bigger for men than women, right? So there's a lot of variation in moral traditionalism among men, some being very low, some being very high, whereas we don't see that much in terms of women, and that's something interesting that we might want to know. Okay, I also created another second continuous variable using a series of questions about would you rather have your kid be obedient or curious, things like that. And these questions come from psychology, and they measure what's called the authoritarian personality, and that is defined as simply a state of mind or attitude or a personality trait characterized by a belief in absolute obedience or submission to one's own authority, as well as the oppression of one's subordinates, right? So widely old, very, very old psychology concept from the 1950s. We can plot authoritarianism on a scatter plot. Here again, we have each respondent, and 1.5 is someone that's high in authoritarianism. These people believe and value authority. Negative 1.5 is somebody who does not. So we get sort of a cloud, right? There's not much we can tell from here. Probably better to do a histogram, right? So let's do that. So I just changed this to histogram, right? And here we get a better picture of where the data lie, right? We can see a lot of people are sort of neutral on this. They value both sort of the authority and sort of the less authoritarian personality, with only a few, about 8 or 9, maybe if we add up all these columns, about 10 people sort of would be classified as having an authoritarian personality. And then what we want to do is see what's the relationship between moral traditionalism and the authoritarian personality. So here, let me just run the plot first. Right? So here we have authoritarianism, higher values equals higher authoritarian personality, higher values here equals more stronger value for moral traditionalism. And so you might want to ask yourself now, are these variables correlated? Now, I would suspect that they are if you think about what each of them means and trying to measure, but do we see that here, right? So what we would expect if the variables are correlated, that somebody who values authority is also someone that values moral traditionalism, and we see that case right here. But we also see lots of people who value authoritarianism, and they don't really value traditionalism, right? Lots of cases here, right? So because this looks more like a cloud, it's very likely that there's not going to be a correlation or any strong real correlation between these two variables. We can test this more by plotting a line here, and this was described in the text. And if we try to do the best fitting line to this scatter plot, it actually goes downward, right? So it shows a negative correlation, a negative relationship between moral traditionalism and authoritarianism. If we run the actual correlation coefficient, now we've been calculating this by hand in some of the homework problems, but here we can just let the computer do it. We get negative 0.21, right? So that's actually a small, modestly relationship. Negative, right? So when authoritarian increases, moral traditionalism is also likely to decrease. So it's not what we expected. But this sort of gives you a sense of, well, when we looked at this picture by itself, all we saw is a cloud. Plotting a line could be very helpful in helping us determine the type of relationship or the type of association or correlation between these two variables. And actually calculating the correlation coefficient is going to give us something that's more precise. And so we generally probably want to add this to our plot. So if someone looks at our plot, they can say, well, there's where the data lies, and we have an exact sort of picture of where of what the correlation is. Now let's look at what happens if we use the wrong statistic and the wrong type of plot with the wrong type of data. So remember, we have moral traditionalism, which is continuous, but we also have vote choice, which is discrete, right? And in the previous example, authoritarianism and more traditionalism, we're treating them as continuous. We didn't run into any problems, right? We were able to calculate the correlation coefficient. Remember, I've written a few times that the correlation coefficient needs to be on continuous data. You don't want to calculate the correlation coefficient between gender and vote choice because those are discrete data, and you're going to get some nonsensical answer. There are other methods to calculate how well discrete data are associated with. But let's look what happened if we do the same thing with moral traditionalism and vote choice, and we just sort of plot those and run a line, right? We get this, right? So moral traditionalism is continuous. It goes from 1 to 5, but vote choice is a 1 or a 2, right, in the data. So this is either Trump or Clinton. And these values are empty, right? There's no way that your responses can take on sort of these values in betweens because so we have this discrete one category or another category. So what that does is it creates all the observations up here and all the observations down here, and you're trying to fit a line through something where a line just doesn't fit very well, right? A line doesn't fit very well. So running sort of a linear line through this type of data, through discrete data, doesn't make much sense. It doesn't fit very well at all, and we're not going to get a good measure of the correlation. Okay. If we looked at moral traditionalism and vote choice using a box plot, there we can actually see a graph that makes more sense, right? So here we see people that value more traditionalism, higher values on this y-axis. They're more likely to vote for Trump or support Trump, and people that have a less value for moral traditionalism are more likely to support Clinton. And we can see the quartile ranges for both of these, and it's larger for Clinton, so there's more variation for Clinton than Trump along this variable. And we don't get an exact measure like a correlation coefficient here, but we can kind of see that there's a relationship here that we might want to explore a little bit further, right? We might also want to look at sort of basic statistics of the data. So moral traditionalism, probably should have did this very early on. We can look at the minimum value is 1, the maximum value is 5, the median is 2.7, the mean is 2.8. So the middle measures are usually somewhat close, but not always, and that depends on the skewness of the data. Okay. We can calculate the standard deviation of moral traditionalism. That's going to be 1. And so what the standard deviation tells us is that 68% of all observations are going to fall within the range of 1.82 to 3.82. Right? And how do I calculate that? Well, I take the mean, right, 2.82, and I add and subtract 1. Right? So that's the standard deviation. And we know from probability theory, which we're going to learn about, that a standard deviation means that about roughly 68% of all observations in the data fall between this range, the range of 1.82 to 3.82. So what that would suggest, if we have 51 observations in this data, that 34 of the observations should fall between that range of values, 1.82 and 3.82. I've looked at the data, and 32 of 51 actually do. So it's not actually correct. It's not exactly right, but it's in the ballpark, right? Most people responded within this range, or at least 68% of the sample did. To calculate the variance, right, we just take the square root of standard deviation. In that case, we get 1. It's going to be the same. And there we could plot moral traditionalism using a density plot. So this is the density, just basically showing us where the bulk of the observations lie. We remember the scale runs from 1 to 5. R implements a smoothing algorithm, so you get some observations that look like it's going to be 0 and 6, but really there's no observations there, right? And we can see that the bulk of the moral traditionalism scale items land just below 3, which is at 2.82, right, is what we get from the mean here. And what I'm saying with the standard deviation is telling us is that about 68% of all observations are going to lie between this value of 1.82, so something right here, to 3.82, to right here, right? And so you draw a line here down, draw a line here down, and we're going to say most of the observations lie in this range of the data. And what I've done here is I plotted what's called a rug, and it's basically plotted little lines where each actual observation is. So these are actual respondents, students in the sample. And we can see that most of the observations do actually lie within that range. And you can see the rug Some of these are light, and that just means maybe one or two people had that answer, and then some of these are dark, and that means that there's actually lots of observations there. So this might actually be hiding like 5 or 6 people that chose, say, 3.2 on this moral traditionalism scale. Um, excuse me. So this is just how we would actually start playing with data or start analyzing data. We take a data set, which is in this big matrix, and then we'd start looking and saying, well, what's the nature of the data? Is it discrete? Is it continuous? That's going to tell us how we should look at the data, what plots we should look at, what measures of central tendency we should look at. And we want to get a feel for each variable in the data set. We want to plot and know what the minimum and max is. We want to know what the standard deviation is and the variance looks like. We want to know where the distributions are. Is there some skewness to the data? Are there outliers to the data that we need to be aware of? And then we want to start by looking at some bivariate relationships. So what's the relationship between gender and vote choice? What's the relationship to moral traditionalism and vote choice? And say if we're going to build a model of vote choice, we start doing this so we can get a sense of, is there anything that might be problematic in the data, an outlier, for instance, that we maybe need to worry about and delete from the data or something. So this is this basic process that I would do with all the variables in the data set before going on to a more complex statistical model.